The most wanted particle of physicists, I think, isn't the dark matter particle. It's the graviton, the quantum of gravity. We don't hear about it a lot because detecting a graviton was for all practical purposes supposedly impossible. Until one day, it wasn't. In the past months, several papers have appeared on how an experiment could detect a graviton. If these experiments succeed, this could lead to dramatic progress in physics. How could it work? And what are the chances? Let's have a look. The graviton is so far a hypothetical particle. It might exist, it might not. Kind of like my motivation before coffee, that's really made of motivons. But what's a graviton? It's a quantum of gravity, just like the photon is a quantum of light. You can think of it this way. Light is an electromagnetic wave, and without quantum physics, that's one big wave, smooth and continuous. But quantum physics says it's really made up of chunks that are the quanta, which are the photons. And a graviton is likewise a chunk of a gravitational wave. How big a chunk depends on the frequency of the gravitational wave, because the energy of the quantum is proportional to the frequency, where the constant of proportionality is Planck's constant. The problem with gravitons, if they exist, is that they mostly just go through us. They interact even less with normal matter than neutrinos, because the gravitational interaction is so very weak. I know it might not feel like gravity is weak if it's preventing you from getting out of bed, but think about it. If your hair gets electric and stands up, that defies the gravitational pull of the entire planet Earth. That's how weak gravity is. If only we could get out of bed that way. That gravity is so weak is why detecting gravitons is so difficult. It's also the reason why it took so much longer to detect gravitational waves than electromagnetic waves, and why ultimately you can't do much with those gravitational waves. How sure are we that gravitons exist in the first place? Well, a lot of physicists think they exist. That's because all other interactions come with quanta, and physicists think it should be the same for gravity. It's kind of like saying, well, everyone else brought a cake, so gravity must bring one too. Not exactly airtight logic, but hey, we've seen worse. I think that's the majority opinion. The minority opinion is that there are no gravitons because gravity doesn't have a quantum version. We'd really like to know what's going on there, because that'd help us solve one of the biggest open problems in physics: how to combine quantum physics with gravity. This is the problem of quantum gravity that Einstein already wondered about, and that has remained unsolved for almost a century. This video comes with a quiz that lets you check how much you remember. Gravitons could be the key to solving this problem. So how do we find out whether they exist? Well, if they exist, they'd occasionally interact with matter. It's just that they do so very rarely because the interaction is so weak. As I said, they interact even less than neutrinos. If you think waiting several years to get 100 neutrino detections is a long time, imagine waiting 10 to the 20 years instead. By that time, even I'll have run out of stupid jokes. What's new is now that physicists are trying to improve the graviton detection by making use of a unique property of gravity, which is that it adds up. More mass means a stronger gravitational interaction, and in contrast to the other interactions, gravity doesn't neutralize. This is why we notice it so prominently. So the idea is that to build a good graviton detector, you don't just need a lot of particles. You need something that behaves like one very heavy particle. They say that this can be done by taking a big piece of metal and cooling it to the lowest possible energy near to absolute zero. At that low energy, quantum effects can spread throughout the metal and make it behave like one big and heavy particle, but one that can ring. It vibrates. If a graviton comes in, that can make the object oh so slightly vibrate, and that's a detection. In a new paper that just appeared, they estimate that if you take about a ton of material and cool it down to millikelvin, then you might be able to catch a few individual photons from gravitational wave events. But you saw it coming. There are a couple of problems with this idea. One is that the biggest chunk of matter that anyone has cooled to that super low energy quantum state is more in the range of micrograms rather than tons. The other big issue is noise. Like, how do you know that the thing that made your detector ring was a graviton? They do make some estimates for background noise in the paper, from thermal vibrations to cosmic rays. One also expects, of course, neutrinos and radioactive decays and the neighbor's dog and what have you. In the paper, they write that similar but improved strategies as for existing experiments would help achieve the required parameters. I think they should think a little more about how those improved strategies might work. And if they can figure out how to cool a ton of material to the ground state, then maybe they can have a chat with those guys at Google and IBM and tell them how to cool all those millions of qubits, because last time I looked, they were struggling to get them into a fridge. As you can tell, I'm a little skeptical, but that's no reason not to do the experiment. I mean, worst case, we have a massive supercooled piece of metal on our hands. And that'd be cool. We've seen a lot of old technologies making a comeback in the past years. Analog computers, for example, which I meant to talk about, but Derek beat me to it. Thanks, Derek. Direct current, which I did talk about, but no one cared. And today we have wheel hub motors coming from a German company that could revolutionize electric vehicles. Maybe. Let's have a look. A wheel hub motor is an electric motor that's directly at the wheels rather than, as we're used to it, in a central engine hub which connects to the wheels. It's moving the action to where the rubber meets the road. These motors were invented already in 1899 by Ferdinand Porsche. Yes, that's the Porsche, because when he wasn't busy designing luxury cars people can't afford, he was literally reinventing the wheel. But wheel motors were never used much. The major reason is that for the past century, almost all car engines were combustion-based, whereas wheel hub motors really only make sense for electric motors. You can't put a combustion engine on each wheel, that'd be insane. So if you use a combustion engine, you need to first create electricity from it and then convert that back to mechanical energy, and that makes no sense energetically. It's really inefficient. But we're shifting to electric vehicles, or at least we're supposed to, which brings up the obvious question of whether the time has finally come for those wheel motors. They are already used for most electric bikes, but the German company Deep Drive wants to go a step further. They have developed a new wheel hub motor that, they say, can increase the efficiency of an electric vehicle by up to 20%. Another way to put this is that an electric vehicle with such a motor, or rather motors, could go farther before you start panicking about where to find a charging place in the middle of nowhere. The increase in efficiency comes from the more direct connection between the power source and the road without a transmission in between. Wheel hub motors have some other advantages too. Most obviously, they save space in the vehicle body, so we wouldn't have to clear trash out of the car all that often. Its proponents also say these motors have a simpler design that makes it easier to fix engine problems. Moreover, if you can individually change the speed of each wheel, that improves road traction. They also have a bunch of disadvantages though. One is the extra weight on the wheels, which isn't buffered by the suspension system like springs and shock absorbers. That's because the suspension is between the wheels and axes and the rest of the car. The weight that isn't buffered by the suspension system is called the unsprung weight. The thing is now that a wheel hub motor, by putting the motors on the wheels, increases the unsprung weight. This means, most importantly, that the motors themselves have to endure more more shocks and that your rides get bumpier. Some other disadvantages of wheel motors are that they get dirty easier and are more difficult to cool. You also still have to control all these motors from a central hub anyway, so that's a lot of cables, and it makes it more difficult to change a tire. Some of these issues can probably be engineered away with enough time, effort and tears, but the biggest issue with these motors is also their advantage, which is the absence of a gearbox. You see, the purpose of the gearbox is to have one fast spinning engine and then convert the engine rotation to wheel rotation. If you don't have the gearbox, you can't do that, so basically the engine spins the same as the wheel. If you want a powerful wheel motor, you need to create a lot of torque directly at the wheel, which has so far proved to be basically impossible. But the German company says they've solved this problem. They did it by using a sort of double motor, really. They use the electric part to spin two rotors, and that way they get more power on the wheel. Better still, they say that they've simplified the brake design, which means there isn't so much unsprung weight added. As you can tell, a lot of this is they say evidence. At this point, it sounds honestly a little sketchy. But this isn't just a design plan. The company has teamed up with BMW, and rumors say a test vehicle has been spotted on the road just a month ago. So this is definitely a real thing. What are we to make of this? Well, as you've seen, on the one hand, there are good reasons to be skeptical. On the other hand, this is technology that hasn't been explored much, so there are probably easy gains left to make. At the very least, it's probably handy for off-road driving. I mean, 4 individual motors have to be good for something, right? Like maybe helping you escape a Jurassic Park situation. In summary, it seems somewhat unlikely to me that wheel motors are going to revolutionize the automotive industry and return Germany to lost glory. But then again, never underestimate the Germans. Maxwell found the equations of electromagnetism 150 years ago, but they still hold some surprises. One of the biggest surprises for me was that only 30 years ago, physicists found a new type of solution that describes a freely propagating vortex ring, which they called a focus donut. It's like a smoke ring, but with electromagnetic waves. The problem was they didn't know how to create it. But in a new paper that just appeared, a group of physicists have shown that they can do it. Vortex rings are fascinating phenomena that we are most used to seeing in water or air. These vortex rings in water contain air bubbles, which makes them visible. Despite their fragile appearance, they are remarkably stable and can travel over long distances. It's the same phenomenon as smoke rings, and as you can see beautifully in this demonstration, these rings are constantly turning inside out. You can see how they form here in a mixture of glycerine and water. This shows a cross-section from the side, which was taken using laser-induced fluorescence. What happens is that the sides of the fluid slow down due to friction and then curl inwards, basically creating this inside-out rotation. Vortices are also often formed on airplane wings, where they can create long tails, but these do not rotate inside out. Airplane vortices are also amazingly stable and can travel quite far distances. Sometimes they drag tiles off roofs or cause trouble for other airplanes. They can even connect, as you can see in this remarkable video, but for today we'll stick with the vortex rings that turn inside out. These ring vortices are what's known as a topological feature, usually formed at the borders of regions, which is why they are closed. The nice thing about these topological features is that they are conserved, so they are very robust to noise. This is also the idea that topological quantum computing is based on, that such a quantum computer wouldn't be so susceptible to noise. You can see why vortex rings would be nice to use for communication, especially when noise might be an issue. The problem is that vortex rings in gases or fluids are usually formed by using some sort of friction. It isn't all that easy to create them for electromagnetic waves because those don't experience friction. And what good is the math if you don't know how to turn it into reality? The authors of the new paper did it by designing a special antenna that has the shape of a cone. They call it an electromagnetic cannon, though if you prefer the technical description, it's a radially polarized conical horn antenna. And it isn't a microscopic device. It has a radius of about 25 centimeters, so it's about the size of a pizza, except if you live in the United States, where pizzas are about 10 times larger. You can see the setup here in a noise-free room. And this is the author's illustration of how the cannon creates the vortex rings. Using this cannon, they were able to generate stable electromagnetic vortices in the gigahertz range. That's about the same frequency range as a common wireless router uses. They measured the field strength at distances of 5, 50 and 100 centimeters and found an excellent match between the theoretical expectation and the observation. Maybe I'm easily amused, but I find this absolutely fascinating. It's not just that they found something new to do with a 150 years old theory, it's also that it could have a lot of applications. And who doesn't love it when some obscure physics discovery turns out to be the next big thing? The most obvious application could be that it's a new method of information transfer. Yes, it uses the same electromagnetic radiation that we already use, but it encodes it in an entirely different way. Maybe there are other advantages to it. Some have speculated, for example, that electromagnetic vortex rings could be used to enhance the resolution of microscopes, basically because that gives you better shape control. And if none of that works, I'm pretty sure someone will find a way to make a weapon out of it. And yes, vortex rings are closely related to vortex streets that are sequences of vortex paths which interlock with each other. They often form in the atmosphere around islands, as you see in this footage. Theoretical calculations have shown that vortex streets can also exist for electromagnetic radiation. Basically, I think this is a discovery waiting for an application. It's the best of blue skies research, and I'm somewhat surprised that so little has been said about it. Either I have a bad taste in research developments, or the rest of the world does. What do you think? Let me know in the comments. Thanks for watching. See you tomorrow.